So till now, we have already seen the single variable optimization. We have also seen the two variable optimization, wherein we use the Lagrange method. So in the two variable case, we have already seen the Lagrange multiplier. We have already seen how the two variable with a constraint case, we have a 3D diagram and how to form level curves with it. We have already seen that the condition that you ultimately get is F1 by F2 is equal to the constraint G1 by G2, which is not an alien concept for us, because when you correlate it with consumer behavior, we are already doing mu1 by mu2 for the utility function is equal to the ratio of the two prices. Now this was the condition coming from the constraint, and this is the condition coming from the objective function, or f itself, which is also called the objective function. Okay, so this we are already used to seeing. Okay, तो ये वाले जो constraints थे ये हमने already optimization में समझ लिया है. अभी we are going to go a step further. We are going to understand कि अगर टू वेरिएबल नहीं, थ्री वेरिएबल का केस आ जाता है, या फोर वेरिएबल या फाइव वेरिएबल या एन वेरिएबल का केस आ जाता है, then how are we supposed to deal with it? Okay, which is very normal, because in economics it's not mandatory that it has to be only two variable or only one variable cases. We can easily get an objective function which has more than two variable cases. Okay, so what happens if I have more than two variable case? What happens is the following. We go on the whiteboard, तो इसको मैं बहुत अच्छे से explain कर सकता हूं. So you consider a function which looks like this. It has n variables, x1 up to xn. Okay, and it has a constraint that deals with uh, supposing only one constraint. Okay, let the constraint be dependent on all the n variables and is equal to c. ओके, तो अगर ऐसा टाइप का कुछ हमारे पास में आता है problem where I need to maximize or minimize this function which is here subject to this constraint, first thing that we do, which we have already learned, is to form the Lagrange. Lagrange कैसे फॉर्म होगा? Lagrange कुछ ऐसे फॉर्म होगा, f x1 x2 dot xn minus lambda by now we are already used to understanding how to form the Lagrange, and वो Lagrange का formulation looks like this. Now we need to basically solve the Lagrange. So if we solve the Lagrange, we'll get basically n first order conditions. Okay, so first order conditions को list करते हैं in this scenario. So basically del L del x1 will be first. So this will be f1 x1 to xn minus lambda g1 x1 to xn. Okay, this is the first one. Similarly, the nth one gives us where obviously f1 is nothing but fi is nothing but del f del xi, and gi is nothing but del g del xi. Okay, so this is what is something that we have now. obviously each of them is equal to 0, right? If you think about it, there are basically n plus 1 unknowns here, x1 up to xn, and the plus 1 is the lambda, which is the Lagrange multiplier. But here we have basically only n equations. So n plus 1 unknowns kaise niklenge? Please understand that this constraint is itself the plus 1 equation. So n equations yahan par hai. This is the n plus 1th equation, which, as I have already explained, can also be put in the first order condition, wherein we do del lambda, del L del lambda, which basically gives us the constraint itself. Okay? So we'll basically get n plus 1 equations, ye n equations, ye n plus 1th equation, and n plus 1 unknowns are there, x1, x2, xn, and lambda, and we are able to solve the n plus 1 equations for the n plus 1 unknowns to get the answer. If you want a more economic example for the same, you can think about n commodities for a particular consumer. So you can consider an example like this, that I have a utility function which would concern n commodities, and I have a budget line which looks like this. So the Lagrange that is hence formed will be utility plus the Lagrange multiplier, and you can get m minus p1 x1 dot pn xn. This is what is the constraint. You can put a plus sign and write it in this manner, or you put a negative sign and do it in the other way. Okay, it's up to you. And then what you do is you do this. First order condition, u1 minus lambda p1, u2 minus lambda p2, un is equal to lambda pn, and the budget line itself is the n plus 1th equation that we get. So n first order conditions along with the n plus 1th equation, that is the constraint itself. Now what you will get from here is the following. You'll get u1 by p1 is equal to un by pn is equal to lambda. You'll get this. Okay. So what is this u1, u2 up to un? This is nothing but the marginal utility. So the utility that the consumer gets, by consuming one extra unit of x1, is this my u1? So the utility that I get by consuming more for x1 divided by the price. So what does this give me? This basically gives me, in money terms, how much extra utility can the consumer get? How much extra utility can the consumer get by spending 1 extra rupee? So by spending 1 extra rupee, how much extra utility I can get as a consumer? That is what this lambda is giving us. We'll understand the economic interpretations of lambda for all these economics problems. But this is only an example where this lambda is basically giving us something called the marginal utility of money. One extra rupee spent, how much is it adding to the utility of the consumer? One extra rupee spent, how much is it adding to the utility of the consumer? That is what this lambda is measuring. So this lambda, which I have as my Lagrange multiplier, is not just some number. It has deep economic interpretations, which we have already understood in the first part of understanding constraint optimization. So it's important for each of you to understand in terms of different economic problems what this lambda will be denoting. The story does not end there. By solving these n plus 1 equations, you are able to find out exact values of my xi's. Okay, there are n xi's, x1 up to xn. Okay, now each one of them is a function of P1 up to Pn prices and the money income. Okay, this is nothing but the demand function for good I. This is my demand function. This is my demand equation for function I. Okay, these are called individual demand functions. Each one of them is called an individual demand function. Okay, that is how much is the consumer demanding for each of these I goods, x1, x2, x3, x4 up to xn. Okay, चलो अब एग्जाम्पल को देखते हैं हाउ टू डील विद द टू और मोर वेरिएबल केस. सो एक जनरल केस ले लेते हैं, अ 3 वेरिएबल केस, सिंपल सा. लेट्स कंसिडर यूटिलिटी फंक्शन केस, वो कॉप डगलस टाइप का यूटिलिटी फंक्शन x into y into z. Let's take that the price for x, y, and z are all equal to 1. Simple sa example. So x plus y plus z is equal to say 9. ठीक है, ये हमने ले लिया. अब इसका लग्रांज हम लोग को करना है फॉर्म एंड सी हाउ टू डील विद इट. सो द लग्रांज इक्वेशन विल बी x into y into z plus lambda into 9 minus x minus y minus z. First order condition, yz minus lambda is equal to 0. This is xz minus lambda is equal to 0. And this will be xy minus lambda is equal to 0. These are the 3 first order conditions. Now, if I solve them from here, I get basically y is equal to lambda by z. From here, I'll get x is equal to lambda by z. And if I put these two equations in the third one, I'll get lambda by z into lambda by z minus lambda is equal to 0. So lambda square by z square is equal to lambda cancels out. So lambda is equal to z square. This is what I'll get. Okay? समझ में आया अब तक? राइट. सो लैम्डा इज इक्वल टू जेड स्क्वायर. तो x का क्या वैल्यू निकल गया? लैम्डा इज जेड स्क्वायर बाय जेड विच इज z. Similarly, y is also lambda by z which is also z. So ultimately what am I getting? X is equal to y is equal to z. ठीक है, put it in the equality constraint. So z plus z plus z is equal to 9. Z is equal to 3. Okay. I am being able to do all this because at some point, somewhere intrinsically, I am making an important assumption. ठीक है. So all of you should have questioned this before I went into this कि सर आपने ये कैसे ले लिया that x, y and z are all non equal to 0? Because z अगर डिनोमिनेटर में आ गया एंड वो इक्वल टू 0 हो जाता है तो ये अनडिफाइंड हो जाएगा, राइट? सो x, y and z, I am assuming they are not equal to 0, because quite clearly if I want to maximize my utility function, अगर x, y या z तीनों में से कुछ भी equal to 0 हो गया, the utility is equal to 0, right? Then it won't make any sense. The utility itself is equal to 0. So I should give some weightage to x, y, and z. All of them cannot be equal to 0. Okay? Each one of them cannot be equal to 0. So x, y, and z are all non-zeros. That is why this entire thing is working. ये intrinsically in the background चल रहा था, जो अगर आपने नोटिस नहीं किया, मैं आपको ये नोटिस करवा रहा हूं कि यहां पर x, y and z आर ऑल नॉट इक्वल टू 0. ठीक है? एनीवे, इसको सॉल्व करने के बाद में वी गेट z इज इक्वल टू 3. सो यूटिलिटी फंक्शन इज बेसिकली x, y and z are all equal to 3. So 3 into 3 into 3, this is my maximizing value. ठीक है? So I hope that each of you can appreciate this simple 3 variable Lagrange problem. यहां पर 2 से ज्यादा वेरिएबल्स हैं and we are using the Lagrange method in order to find a relationship between x, y and z, and then substituting that in the main constraint itself, that is giving us the answer. ठीक है? Now, obviously it's not outrightly clear कि why is this 333 the answer of the maxima. Okay, we are taking that this is the maxima because there is a minima possible where one of them is equal to 0. x, y या z तीनों में से कुछ भी अगर 0 हो गया, यूटिलिटी तो 0 है, एंड ऑब्वियसली 27 इज ग्रेटर देन 0, तो ये तो मिनिमा तो हो नहीं सकता है. एंड you can only be sure after you check the sufficiency conditions or the second order conditions. Now, the second order condition in even the 2 variable case was quite complicated. So the 3 variable case will be a completely different ballgame. Okay, you will take a calculated and understanding guess that this is a maxima. ये guess नहीं है, guess wouldn't be the right word to put here. You are actually seeing this. You have understood that x into y into z will obviously be maximum when all of them are equal, when x plus y plus z is equal to some constant value, right? अगर वो equal नहीं है, you will get lower values. You can take different values and check. So if I consider 5 to 2, 5 into 2 into 2 is giving me only 20, जबकि यहाँ पर क्या था, 27 था. You'll see that if I give equal weightage to all of them, you'll get the maximizing value. ठीक है? This has to be understood by looking at the function itself, looking at the constraint. So you have to take a calculated understanding guesswork that this is the maximum value. Okay, तो ये तो सिंपल सा एग्जांपल था जहां पर 2 वेरिएबल्स से ज्यादा वेरिएबल्स हैं एंड देयर इज ओनली वन कांस्टेंट, राइट? इसने बोला कि खाली एक कांस्टेंट हो सकता है. Let's consider a general case जहां पर you have a function which is n variable. We'll call this the general case. जहां पर the function is having n variables and you have multiple constraints. Okay, so first constraint, I call it g1 is equal to say c1. I'll get g2 is equal to C2. So you have multiple constraints that are possible. Okay. This can be seen by looking at this. So one maximizing or minimizing problem subject to multiple constraints. G1, H1, multiple constraints can be this, can be there. Now it can be equality, it can be inequality, but currently we are only thinking about कि inequality नहीं equality वाले constraints को लेकर अभी चल रहे हैं. Inequality constraints will be best understood once I go into the Kuhn-Tucker methods. Okay. So let me explain that ये multiple constraints आ जाते हैं तो हम लोग को क्या करना है. So we'll understand that right now. Okay. So let's understand the multiple constraint case and how to form the Lagrange out of this. So यहाँ पर let's consider that there are m constraints. So the Lagrange can be written in this particular fashion. Okay. 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 This can also be written in a general format. General format में इसको ऐसे लिखा जा सकता है. Summation j is equal to 1 to m lambda j gj n variables minus cj. Okay. इसको ऐसे लिखा जा सकता है. नाउ कितने फर्स्ट ऑर्डर कंडीशंस होंगे इसमें? कितने फर्स्ट ऑर्डर कंडीशंस होंगे? There will be n first order conditions. I'll differentiate with respect to x1 up to xn. So n first order conditions होंगे. So del L del x I. Basically for I is equal to 1 to n first order conditions होंगे. वो कैसे दिखेंगे? Where f is this function minus j is equal to 1 to m lambda j तो lambda j ही रहेगा. Del g j having the arguments x1 to xn del xi, this part is equal to 0. So this is the first, this is how each of the constraints will look like. ये तो this is a generalized del L del xi, I is equal to 1 to up to n. ठीक है. So n first order conditions आपको मिलेंगे. अब n फर्स्ट ऑर्डर कंडीशंस हैं, इसके साथ साथ में देयर आर m constraints. सो m constraints है. कौन से m constraints है? g1 is equal to c1, g2 c2, gm is equal to cm. ये m constraints हैं and n first order conditions हैं. And how many variables do I need to find out? I need to find out x1 to xn lambda 1 to lambda m. So there are n plus m unknowns to be found out as well. Right? So if we have to maximize or minimize an objective function with respect to multiple constraints, each of the constraint will represent a different Lagrange multiplier. And the first order condition that I get will be having n equations. And the constraint itself will give us additional equations, and that will combined give us the solution to the entire Lagrange problem. Okay. So what have we understood in the general case? General case में सबसे पहले we started off the n variable case with only one constraint. So we started off with that. We did a problem with that. But why are we restricting ourselves with only one constraint? We can have multiple constraints. उसके साथ में कैसे डील करना है? ऐसे डील करना है. Now it can be a good time to go into a problem with multiple constraints. चलिए एक problem को देखते हैं with multiple constraints.